10.3 Titrations. A titration is a procedure used to determine the concentration of a solution using a standardized solution. The titrant is the solution in the burette during a titration, and the burette is a calibrated tube used to deliver the variable known volumes of a liquid during a titration. Figure 1 shows the titration of sulfuric acid in the flask with sodium hydroxide in the burette, using bromthiamyl blue as our indicator. The chemical equation for this reaction is as follows. Sulfuric acid plus sodium hydroxide produces sodium sulfate, a salt, and H2O, water. Remember, all neutralization reactions produce salt plus water. So we have the titrant inside the burette, and we have a receiving flask with a sample, and inside we placed bromthiamyl blue, which is an indicator. As we add the liquid drop by drop, the titrant drop changes the indicator color momentarily, and you can see on the surface we slightly start to change this. But if you were to swirl this beaker around, it would remain yellow. The end point is the last drop of the titrant that changes the indicator color permanently throughout the flask. If you were to shake this or swirl it around, you would no longer see this yellow color. We have permanently changed the color of the liquid in the flask. If you add a second drop more after the end point, then the color will turn to blue. The equivalence point is the point in the titration when neutralization is complete, and the end point is the point during a titration when a sudden change in observable properties of the solution occurs. It usually a change in color as the acid-base indicator or a significant change in pH. Let's do an example where we determine concentration using titration data. Several 10 milliliter samples of sulfuric acid of unknown concentration are titrated with a 0.100 mole per liter solution of sodium hydroxide. Note that the burette contains the sodium hydroxide. The end point was determined using phenolphthalein indicator. The acceptable observations from the titration are summarized in Table 3. Use these data to determine the amount concentration of the acid in solution. First thing we want to do is calculate the average volume of titrant used. So if you look, we have 3 different volumes used in the 3 different trials. So the average volume of sodium hydroxide, our titrant, that we used for the titrations to reach our endpoint were 12.42 milliliters, 12.46 milliliters, and 12.52 milliliters. The difference in these values most likely relates to human error and our inability to stop the drops from falling in precisely. We'll divide this by 3 to get our average sodium hydroxide value of 12.47 milliliters. Now we want to convert the given volumes to liters. The volume of sodium hydroxide is 12.47 milliliters times 10 to the power of -3, we end up with 0.01247 liters of sodium hydroxide. The amount of H2SO4 in each of the samples was 10 milliliters, or 0.01000 liters. Next, we want to write a balanced equation for the reaction listing the given values, the required values, the molar masses of solids, if any, and amount concentration of solutions below the entities considered. So we have 2 NaOH plus H2SO4 produces Na2SO4 plus 2H2O. We know that we have 0.01247 liters of sodium hydroxide for 10 milliliters, or 0.01 liters of H2SO4. We know the concentration is 0.100 moles per liter, and we need the concentration of H2SO4. We're going to use the concentration equation to determine the amount of the substance whose volume and concentration are given. So we know the concentration of sodium hydroxide is the number of moles divided by the volume. So the number of moles is equal to the concentration times the volume. That's 0.100 moles per liter times 0.0124 liters. And we end up with 1.247 times 10 to the power of -3 moles of sodium hydroxide. I'm going to write that down. In step 5, we're going to use the amount of substance determined in step 4 and the mole ratio in the balanced equation to determine the amount of the required entity, the number of moles of H2SO4. So we have a mole ratio of 2 over 1.247 and 1 over the unknown. If we rearrange to solve for the number of moles of H2SO4, it's equal to 1.247 times 10 to the power of -3 moles divided by 2, which equals 6.233 times 10 to the power of -4 moles. We're going to use the amount of moles determined in step 5, the volume of substance required, and the concentration equation to determine the amount concentration of the required substance, H2SO4. So the concentration of H2SO4 is equal to the number of moles of H2SO4 divided by the volume of H2SO4. That's 6.233 times 10 to the power of negative 4 moles divided by 1.000 times 10 to the power of negative 2 liters. If we punch this in, we end up with a concentration of 6.233 times 10 to the power of negative 2 moles per liter. Therefore, the amount concentration of the sulfuric acid is 6.233 times 10 to the power of negative 2 moles per liter. Please try any practice problems assigned, as well as any LMS videos on this section.